Hello, sir. Shall we
Oh,
start?
okay, sir.
Okay.
Okay, please start.
Good evening to all of you once again. So yesterday we were discussing several things related to polynomials, some basic complex analysis, etc. So as per the workshop schedule, today we are supposed to discuss something related to abstract algebra, like uh, doing some computations in groups and permutation group, dealing with permutation groups, cycles, etc. And since the multiplying permutations and splitting them into cycles, all these things are a little bit difficult if you do it manually. And let us try to see that how we can do all these things using Sage. Not only that, we will try to see how to solve polynomials. We have of course already seen a little bit of those things. How to solve polynomials in different fields, different abstract fields. That also we will try to revise once again. Let me share the screen. And here is the link to Google document with commands. In fact, yesterday and day before yesterday itself, we have seen how to create the very common, very basic finite groups. In fact, those are the standard finite cyclic groups in abstract algebra. They are integer modulo rings or congruent strings. So to create that, there are actually several different commands available, and one of the most simplest thing is probably going to be the command using integers. Okay, let us start with that, and after that we will go to new topics. This is actually something that we introduced yesterday itself. So if you want to create, for example, Z file, simply we write integers file. Now, if you want to list the elements, if you simply ask for printing Z file, we'll just give the ring of integers modulo 5. But now, if you want to see the list of elements in that, we need to list. Now there is a possible confusion that the elements look actually like 0, 1, 2, 3, etc. But if you actually take one element and ask for what type of element it is, for example, suppose that we take A to be equal to, or A naught to be equal to the first element in this list. The first element in this list is accessed using, I myself don't know, probably this symbol. What is A0? Let us ask. A0 is 0, and what is the type of this? A0. If we ask for, we will get the type to be class Sage rings, finite rings, integer modulo, integer mod in. Therefore, this is not a straight away an integer, but this is something else. But can we perform other operations on this A0, like multiplying, taking the power and all these things we can do, but can we multiply it with the usual integer A0 plus 2? What will happen? A0 plus 2 returns 2. What about A0 plus 5 or A0 plus 6? So here the operation automatically A0 plus 6 is nothing but 6, because A0 is taken as the 0th element. If you take A0 plus 6, what happens is the plus actually becomes the usual what you call integer modulo operation. But instead of that, if you try 0 plus 6, the result is just 6. Okay, now you can see what exactly Sage is doing. Whenever it detects an element from one particular ring, it tries to convert the other element also, if possible, to element in the what you call the finite ring. Now, suppose that if we mix up these things, suppose Z6 we take. Let us see what happens. Integers 6 and take B0 equal to Z6 0. Suppose we add A0 plus B naught, what will happen? Now here is an error, because the problem now is that we have two elements from different rings. That's not allowed. So element from the 6 is automatically taken as an element in Z5 itself when it detects another element in Z5. But if we mix up in such a way that there is a confusion, it will not give any result. Elements from two finite, two congruence groups. This is wrong. Let me update the Google sheet with all this update. Now power and everything we can do as usual. Let us take A0 itself, not A0. Let us take A1. A1. Or instead we can use Z51. Print Z51, Z51, not Z52. We will take Z52 to the power 3. Z52 is nothing but 2 itself. 2 to the power 3 is actually 8, but modulo 5 it has to be 3. But we should suppress this. That's 3. So that exponentiation is working as usual. As I told, Z5 to the power, Z5 of 2 to the power 3 is taken, and then it is taken a modulo. That's what happening here. Okay. Now we can find the, so Z5, we know that it's 2, and the additive order of Z5 simply means that the smallest number of times it needs to be added to the number itself so that it will become the additive identity 0. So additive order 5. Additive order of Z5 to, oh, it's it just gives maybe is. Two is 5. So we can list the additive order of all the elements like this if you prefer. So for I in or otherwise for x in Z5, print the additive order of each. X. Two is 5. So what is 2? So 2 is the first element. Okay. 2 is 5. Then after that 0 is 1. 1 is 5. 2 is 5. 3 is 5. And 4 is 5. And we know that. So all these elements are actually 1 is the generator, 2 is the generator, 3 is the generator, 4 is the generator. All these elements are generators basically because we know that in Z5 any element that's relatively prime to 5 any element in Zn that's relatively prime to n will be a generator. So we can actually write a small very short program for finding out all the generators just using the GCD condition, right? Or using the what you call additive order condition. If the additive order of that element is equal to the size of the cardinality of that set itself, that in that case we may say that that's a cyclic group. That's a way to determine that. Or find all generators, because we know that all the congruence rings are cyclic. Suppose we take n to be equal to 5, integers modulo n to be equal to 9, G, list G. Now removing all this, so cardinality of G, will this work? I don't know. I guess it should. cardinality of G is 9. Let me use this symbol. For X in G additive order of, and we can also say that if the additive order of X is equal to cardinality G, then we will simply say that X is generated. X is the generator of G. That's it. So 2 is a generator, 4 is a generator, 5 is, 7 is, 8 is. So if you want to take all these if you want to push all these generators to a list, maybe we can even do that in this way. Append X, and finally show the generators everything together. Generators are 1, 2, 4, 5, 7, 8. Updating the Google document. Right. So in this example, we found we listed all the elements, all the orders, and finally we found the generators also. Now the multiplicative order yesterday itself we have seen, that also we can try. And the multiplicative order, remember that this is applicable provided that GCD of an element with n is 1, using same example. But remember that here we need the condition that for X in G and GCD X and cardinality G, this is equal to 1. Otherwise the multiplicative order does not make sense. Multiplicative order of X is multiplicative order. Why is this not working? Just 1 second. So what is the command that we used? X dot multiplicative order of X, if X in G and GCD of X and cardinality of G is equal to 1. What is the error here? This is not iterable. What is meant by that? X in G. Oh, that's not correct. X in G, probably I should split it. If I think this is the correct way, I don't know, I'm just trying. Yes, that's working. So I cannot use X in G, and this is not a valid thing. Otherwise, what I should do is for G in, maybe something like this. I should create a sublist. X for X in G if GCD of X and cardinality is 1. This is possibly one possibility. Yes, that's also working. And we may actually push this to multiple unit group, units G. If this condition is satisfied, that means the cardinality is 1. Let us push this X to, no, G to this. And print finally this is the unit group 1, 2, 4, 5, 7, 8. So this is finding units in G. The Google document is now updated. Okay, this is how we filter all the units. Now the group table or the Cayley table, though we have already seen this thing, so there is an easy command as well. So to find the addition table, what we can do is we can simply use one simple command instead of using the complex for loop or more lines using for loop. We can simply write, so what is the ring that we have taken here? G is equal to this one, and n equal to 9, taking SageMath. So we can simply print G dot addition table. But see that here what happened is G is the elements in G is not very clear. Therefore, the addition table it simply uses symbols A to E, A to I. So now, instead of using such notation, what we can say is that use the elements itself as names of whatever. So the representation of elements is using some random symbols A, B, C, D, E, F, G, H, I. Instead of that, we can specify so we have seen if you do not use this command, what will happen, and if you do use this command, what will happen. And can we form the multiplication table? We can try. I myself don't know, I am just trying. So both these tables are possible, multiplication table as well as addition table. So updating the Google document. This, as we know, this is usually known as the group table, or so can we do exactly the same thing in the case of what do you call the units? Let's try to do that. N equal to 9. Cardinality is here, units is here. Now, what do? Print units G that's not happening because it's not actually a Sage defined object.
In the previous table, how to get the numbers like 0, 1, 2, 3? What is the input I should give?
Is that what you are asking for?
Yeah, to get the number like 0, 1, 2, 3, so on. What is the thing I have to do here?
Elements I have used. Names equal to elements. So name the name of the elements you should use as the elements itself. Otherwise, it's using some symbols like A to I.
Sorry, sir, I couldn't get it.
See, if you do not use this, if you do not use this names equal to elements extra parameter, what happens is Sage is listing the elements as A, B, C, D, E, F, G, H, I.
Okay.
But if you use names is equal to elements as the extra parameter inside the addition table addition table command, the 0, 1, 2, 3 is used to label the elements.
Okay.
So this is the extra parameter we are passing.
Okay, sir.
In both multiplication table as well as addition table.
Okay, sir. Thanks.
elements command it understand, and it takes the elements in that exactly the elements in that ring for constructing the group table. That's it. There are different of element commands, like module element is there, ring element is there, several things are there. So not all of them we are going to discuss. Of course, we can go through that the documentation called parents and elements. There is actually a very good help file. It's not actually that straight away, but you can find some examples using that. Some examples, some very good examples are there. Okay. Yeah, there is actually one more thing I want to just tell, that the division, whether it takes place or not in an integer group. So this is not working. As we have already seen, we may list the elements like this. The elements are listed here. Now, one thing that we can ask is, which of the elements are multiples of their elements? That we can actually ask. Okay, that's unless we find E square polynomial that we have already seen in mode. Okay, so let me just go into the other thing. Now we can define the symmetric group. So the modulo integer ring we can define like this, and the unit group also we can define like this. But the thing is that the unit group, if we define, so that unit group that we are defining it as a list. Unit group integers. Let me just see if I can tell something interesting. Okay, let us go into permutations, and after that probably we will try to see what are the. Okay, this I'm just going to the permutation groups now. Now for defining the permutation groups, the command that we have to use is symmetric group. Okay, let us define Sn equal to symmetric group n, where n, let us define it to be n equal to 3 or n equal to 1 itself as the first example. If we try, let us ask what this is. Symmetric group of order 1 factorial as a permutation group. If we go for n equal to 2, we are getting this answer. Now try with listing the elements. What will you get? So we will get the empty bracket, which probably denotes the identity element. There is nothing in that. And 1, 2 is the other non-trivial permutation. Let's do this again. Equal to 3. Empty. So we expect 6 elements to be there, or cardinality. Number of elements 6. We can say that the elements are listed as tuples. So if you want to take a specific element, if you want to define a specific element using the whatever, suppose that you want to define the permutation 1, 2, 3 going to 3, 1, 2. Okay, so we have already taken n to be equal to 3. Suppose we want to define the permutation 1, 2, 3 going to 3, 1, 2, say. Then what we have to do is we have to make use of this Sn. So should I use Sn? Okay, Sn itself. So usually we define, or 1, 2, 3 going to, so this is actually a 1, 2, 3 going to 3, 1, 2. This is actually a rotation. So let us use the symbol. Rotation 0 is nothing but 0 rotation, I think. So rotation 1 is 0 rotation. So 1, 2, 3. This we call, shall we call this as rotation 2? Rotation 1 is 0 rotation, rho 2 equal to Sn in bracket 3, 1, 2. Is it the same as 1, 3, 2? Is it correct?
So it is not the same.
No, that's what I'm checking. So what is the meaning of this 3, 1, 2? 1 going to 3, 3 going to, so what do you mean by writing 1, 2, 3 going to 3, 1, 2, 1, 2, 3, 3, 1, 2? It essentially means that 1 goes to 3, 2 goes to 1 and 3 goes to 2, right? So the meaning of this is, this essentially means that 1 goes to 3 and 2 goes to 1 and what is the last one? 3 goes to 2. Okay, so in the cyclic notation, how do we write this? This is actually a cycle. Okay, because 1 to 3, 3 to 2, 2 to 1. So this is 1, 3, 2. Do you agree with that? This element. Here 1 is going to 3.
These are images. Actually, we want to show that image of 1 is 3. Oh.
Isn't it? This is cyclic notation.
Oh.
This notation is given as a cycle. Then it's correct, right?
Yes.
Sage is returning it as Sage tries to represent everything as everything either as cycle or as product of cycles. That's what's happening here. So maybe we will try something else.
Sir, cannot get what that the 3, 1, 2 means. It is mapping that using that Sn function.
See what I wanted here is 1, 2, 3 on the top row and 3, 1, 2 on the bottom row. That's what I wanted, right?
Okay.
So which essentially means that 1 is actually going to 3, 2 is going to 1,
Right.
3 is going to 2.
Exactly.
So 1 to 3, now 3 to 2, and 2 to 1. That's a cycle, right?
Yes, sir.
So rotation is essentially a cycle.
Yeah, rotation is cycle.
Yeah, we are rotating. So Sage is returning the element back to us as a cycle.
With rotation in which direction?
A rotation in the in one direction only we usually take, but the other direction I don't think that we call it as rotation. But on the other hand, we call it in some other. So what are the elements? There are 6 elements, right? In symmetric group n, symmetric group 3. So the first element is 0 rotation. Second element is rotation in the rotation with how many degrees? Third, I think 60 degrees. Second is 120, and when we go not 120, so 120, 240 and 360, these are the rotations, right, in the anti-clockwise direction if we have the group of symmetries.
Okay.
Suppose that we label these elements as the vertices of a triangle. That's how we create S3. Then we have actually a symmetric, not symmetric, what do you call that, not isosceles, what is the name of that triangle with all sides equal? Equilateral. Sorry, I immediately quickly forgot that. Equilateral. Yes, correct. If we are taking an equilateral triangle where the degrees are all the sides are equal, therefore if you rotate the triangle and if you want one vertex going to the other vertex, then you should rotate it by 120 degree or multiples of that. Okay, then only one vertex will move to the other vertex. See, think of the triangle picture. Triangle picture, which is an equilateral triangle. If you rotate the triangle, so in 3 rotations, it should come back to the original position. Therefore, each rotation must be of 120 degree. So there are 3 rotations essentially. So you take it in the clockwise direction or anti-clockwise direction, it's up to you to define. So if you take the clockwise direction and if you define it in the anti-clockwise direction, most probably you will be getting 2 different groups which are isomorphic.
Okay.
So you need to actually fix that in which direction. That's what I think. I don't exactly, we have to check all these things if what I'm saying is correct or not. But what I believe is that this is going to happen.
So, sir, so here Sn, so the row 2 we have defined Sn312. Means that do you want to know where the function is mapping, something like that?
No. I have. See, first the top row is not needed to be defined because we are in S3. The top row is always 1, 2, 3.
Okay.
Only the bottom row we are defining.
All right.
So 1, 2, 3 goes to 3, 1, 2. That's it. So 1 to 3, 3 to 2 to 1, 3 to 2.
3 to 2.
Yeah, that's
right.
That's returned as a cyclic notation 1, 3, 2.
Okay. Yeah, sir. Got it.
Maybe we can try with some other instead of row, sigma. I think that's the name we use for the reflection, right? A row was reflection, a row was rotation, and what is the notation we use? Okay, let us use sigma for the time being. So sigma 1. Suppose we reflect 1 and 2 each other. So 1, 2 becoming 2, 1 and 3. Okay. If you print, okay, this is nothing but in cyclic notation 1, 2. Because here 1 goes to 2 and 2 goes to 1 and 3 is fixed. Fine. Now, if you want to list all the elements in S3, that also can be actually done. Print. List S. So, okay, that I think we have already done. Sorry, that's not necessary. We already have done that. So, the six elements are listed as 6 cycles. 1 3 2 1 2 3 1 going to 1 going to 1 2 2 going to 2 3 going to sorry, what is meant by this 1 2 3? This is empty. What is meant by empty? What is meant by 1 2 3? 1 to 1, 2 to 2, 3 to 3, or what exactly is this? 2 3, so 2 and 3 are rotated. So what is meant by this 1 2 3? So this is zero element number 0 1 2, right? So let us ask what this
Identity permutation.
but what is that empty bracket then?
And identity permutation means 1 goes to 1, 2 goes to 2, 3
No,
goes to
no, there are 6 elements, right? So what is this then? Already we
Yes,
have.
sir. It is the identity.
6 elements are there, yes. 6
So-
elements are there.
Yeah, identity.
Identity permutation, and then
Okay, 1 to 2. So right. Sorry. That's a mistake. 1 to 2, 2 to 3, and 3 to 1. That's the third element. Third element is in cyclic notation. So I am talking about the element that's highlighted here. This is 1 to 2, 2 to 3, and 3 to 1. That's the cycle.
yes,
It's not 1 to 1. So again, got confused with 1 to 3 and 1 to 3. It's not 1 to 3 going to 1 to 3, but on the other hand, it is 1 to 2, 2 to 3, and 3 to 1. So maybe we can just try to 0 1 2. This is second element. So what is the second element? The list is not working. So maybe can I use this? I don't know. That is just 1 2 3. If I try to list the elements, now it is shown in cyclic notation. If I use the list notation, okay, that's also not much useful. This is 1 2 3 only. So the bottom row is okay. 1 3 2. Print S and 2. 0 1 2 1 2 2. So it's not listing as 2 3 1 somehow. But what about here? If you list this,
2 3 1 is the same as 1 2 3.
no, what I'm thinking is
the same as 1 2 3.
here we fed the value to be SN 3 1 2. Okay. Row
3
2.
1 2 is the same as 2 3 1.
No. What I'm asking is we fed the value here. We gave the input as 3 1 2. Here
3 1 2 is the same
I
as 1
agree.
2 3.
I agree with that. But the way in which we gave the input as the bottom row we gave us 3 1 2. I am trying to get the bottom row instead of the cyclic notation, the bottom row. So if I want to get the bottom row, if 1 2 3 is
We have to write images of these elements.
exactly, I want the image of 1, image of 2, image of 3. Exactly. So can I?
We take this element as A and we write A of X. A of X.
Let us try to see if the A of 1 in this is working. That what is this element? Which is that third element? 0 1 2. The second element we want. Okay. Let us call this element as A. And let us see if A of 2 or A of 1. Yes, A of 1 we get as 2. Or if I try and if I print this, no, just the same notation. A of, what is A of 0? Why am I still getting it equal to A equal to SN2 I assigned, but what is A then? Image of 0, it gives just this.
A of x. A of x.
Sorry, A of
X.
X means what?
X. X in 1, 2, 3. Image of 1 and yes.
Image of A of 1 is nothing but
X,
okay.
X
A
in
of
1, 2, 3.
right. This is correct. A of 1 is this is correct. A of 1 is 2. That's correct, right? A of 1, A of 2. Oh, sorry. A of 2, A of 3. If we keep everything inside the tuple, the element is here. A is this. So by 1, 2, 3, we actually mean 2, 3, 1. 1, 2, 3, 1, 2, 3, 2, 3, 1. Correct?
Yes, sir.
So 1, 2, 3, 2, 3, 1. That's what 1, 2, 3 means. Okay. Now I think it's clear that the notation Sage is using is it's quite clear. So this is how we get okay. The reflection, I think the name we use was mu, not sigma. I completely forgot what exactly the notation was. Anyway, we haven't tried this. So reflection 1, this is mu1, that's 2 to 1, and reflection 2, what is reflection 2? I think 1 and 3, Sn with bottom row 1, 1 and 3 we're getting interchanged, right? So 3, 1, 3, 2, 1, right? That's the correct notation. 3, 2, 1. The bottom row is this. So 1 goes to 3 and 3 goes to 1. That's correct. The original one is reflection 1. 1 goes to 2, 2 goes to 1. So the last one is nothing but 1 is fixed. 1, 3, 2. That's reflection 3. 1, 3, 2. So 2 and 3 gets interchanged. 2, 3. Cycle 2, 3. So these are the elements. Now can we multiply? That's okay. See, I hope that this is clear. So let me update the Google document. Update. Okay, so this is how we we can actually use this type of notation, this type of product notation we also can use. So okay, to find the inverse of this thing, that's also quite possible. We can find the inverse of rho also. So we continue in this same thing. Maybe since we have already defined, okay, I will use the notation sigma 3 itself, which is a very good example for us. Sorry, S3 itself. Let me write S3 equal to symmetry group 3. Now row 1 as previously. Row 1 is the identity, it seems. Row 2 is this element. Row 2 is here. Inverse, can we find the inverse directly using the inverse notation? So can we multiply also? Empty, which corresponds to the identity one. So we can find the inverse straight away by using the inverse notation to the power minus 1. Now the 1, 3, 2, the order of this also we can find, and before finding the order of that, maybe we can in a loop. Let us try to see, since we know that S3 the cardinality is 6. We know that if we take if we multiply that with the same element 6 times, we should definitely get identity, and before we should actually, because S3 is not a cyclic group. 4 I in range S3 cardinality, or maybe we can equate with identity itself. I don't know how to actually give the identity. Maybe we can simply give it as an empty list. So how do we notate the identity matrix, the identity permutation? IDN equal to S3 0. Will it work? Probably yes. So as long as this is not the identity, we will try to take the powers. Let us try to see if this is working. 4I in range maximum 6, because that's a cardinality. So ith power of row 2 is row 2 raised to the power I. What is this? Okay, sorry. Already the cardinality is there. Zeroth power is there. Okay, 0 we don't actually need. 1, 2. 1, 3, 2. So we can see that this is becoming here. So maybe when it becomes the identity, we can stop. If equal to IDN, we may declare that we have found the order. Order of row 2 is I, because we found, and break the loop. No need to go further. Third power, the TH is not necessary. First power is 132, second power is 123, third power is. So the order is found like this. And this is not actually necessary. We can directly also find the order using the what do you call order command. Since this is the group, the order command will work, and row 2 order is given as 3. Okay, so this is how we can find the inverse, we can find the cardinality using for loop, and we can find cardinality, we can find the order using for loop, which is not necessary because already we have the order command with us. So I am updating the Google document. Okay, now we can multiply the groups in the following way. So multiply the elements in the following way. So for example, suppose that we want to multiply, we want to take instead of directly taking element from that, so instead of looking at the list of elements in that S3 and using the notation given inside that, we can directly also multiply like this. Sigma equal to S3 is the notation that we used. S3. So simply in quotes, let us give. So if you want to multiply 1, 3 and the usual notation and 2, 3. Oh, sorry, we should use comma here. We didn't use comma here. What I did? Two, 5. Okay, let me just try to see. Okay, so 1, 3 and 2, 3. Why is that not working? 1, 3 and 2, 3. Two, 3 essentially means that 1 is going to 3. So if I use 1 to 3, which means 1 to 2, 2 to 3, etc., will it work?
star means for multiplying two elements.
No, that's okay, but for using star, what you have to do is that you cannot use the notation 1, 2, 3, right? Because you need to declare an element row 2 as SN312. You cannot, yeah, I'm trying to do it directly.
Oh,
So this is quite valid. This is perfectly valid. If you define row 2 to be equal to SN312 or SN even 31, I don't know whether SN even 31 will work or not. Let's try to see. This is S3. S3. Suppose we do it like this. Star 31, will it work? Bottom row, I think we need to completely specify, because otherwise it's no, we need to completely specify this bottom row 312. This is working. But I was thinking that this also should work, but this is somehow not okay. Probably that my notation is probably not correct. I should probably give it as disjoint things. So I am not giving it as. Oh, sorry. I am not. I got confused with some other thing. Okay, let me just take another example. This is perfectly correct. So instead of this, this should work. I can give it as a product of disjoint cycles like this. 1, 2, and then 3, which is essentially the identity permutation. Okay, this makes sense because 3 is already the identity. See, since we are in S3, we do not have too many things to experiment. So let us just move to S5, which is something with more symbols. Okay, let me just update everything typed here in the Google document. So updated. It take S5 instead. So if I use S5, this notation makes sense. S5, 1, 2, 3, 5, 4. Oh, sorry.
S5, yes. So
Yes.
symmetry group 5, yes.
It's correct, right? Now this is correct, right? So this is one. So instead of the symmetric group, we can actually create the notation called permutation group. Is also that notation is that command also can actually be used. Permutation group. Let us P5. Let us see if these two are same or not. or maybe we can, yes. Oh, sorry. In fact, permutation group can be used not for this. Permutation group is actually we can use. Okay, let us just try to the S5. Let us take it to be this itself. Okay, sorry, there is a small confusion with me. So suppose that we use the list the elements in S5. So let us list S5. List the elements in S5. So 1, 4, 3, 2, 1, 2. Okay, so let us choose the element 1, 2. Is there any element 1, 2, 4 and 3, 5? Let's suppose that we take this element. An element G equal to S5 in quotes this. Now I need to list this. So 1, 2, 4 and this. Now suppose that we define permutation group using two elements from this. So what is the output? Let us see. H equal to permutation group. So previously I copied this. So this is one element G, and suppose this is G1, and suppose now G2 is nothing but 1, 3, 4, or just 1, 3, 4. I don't know whether that makes sense. 1, 3, 4. Oh, sorry. Print G1, G2. So this is perfectly valid. Now suppose that we define we take G1 and G2 here, and suppose now what this H is? G1 okay, we need a list. Let us keep it as a list of generators trying to generate instead of doing this. So generate permutation group is the so it's this. So we have generated a permutation group with generators 1, 2, 4 and 3, 5. On the other hand, suppose that we take just 1, 2. Okay, suppose that we take to be simple enough. Suppose we take just 1, 2. So listing of the elements. So identity element. So we can generate subgroup. So we can specify any number of elements in this, and using these elements, permutation subgroup will be from the symmetric group S5. Permutation subgroups will be created using the generators with G1 and G2 are generators. Let me update the Google document with this. So here essentially we are create by specifying the generators. This is what we are trying. Now we can even retrieve the generators like this. So in fact, we can retrieve the generators from generators of even S5. Remember that S5 is not a cyclic. Even S3, S3 onwards, none of these are cyclic. None of these are actually abelian also. So we may retrieve the generators using the gens command. S5 dot So 1, 2, 3, 1, 2, 3, 4, 5 essentially means that one going to 2 going to that cyclic one, and the 1 to 2, 2 to 1, that element. So using these elements, S5 can actually be generated, is what Sage says. So if you look at, if you take H1, okay, that does not make. In fact, we can find the degrees of all the generators also from this S5 gens command. So if you want to see the degrees, the orders, not degrees, all the orders of the generators. So gen S5, suppose we use this command, then let us try to find all the orders for gene. Maybe even directly we can do this. G dot order. Order of G. So these are the generators. Generators of S5 are these. And the orders are these. 5 and 2 respectively. Order 5 and order 2. So updating the Google document. Now, in fact, we can construct the group table also like this. Just as we have done, instead of additive group table, additive multiplicative group table commands that we have used here, we have to use the Cayley table name for constructing group table. Let us take the symmetric group S3 for simplicity. Symmetric group of 3 elements, and print Cayley table. So print Cayley table. So what will happen here is that it again gives the name like A, B, C, D, E, F, because there are S3, there are 6 elements, 1, 2, 3, 4, 5, 6. But instead of that, if you want to see the permutation names itself, we may use names equal to elements. The group table is here. With the permutation multiplication as the default operation. But on the other hand, suppose that you want to identify this these elements 1, 2, 3. Suppose that you want to identify. Okay, can we get the LaTeX notation as well? I don't know. I'm just trying. Okay, we may even get LaTeX notation so that if you want to copy and paste this into some document that we are preparing, you may even use that. Okay, what I'm saying is, so instead of this empty bracket 2, 3, 1, 2, 1, 2, 3, 1, 3, 2 notation, suppose that we want to label the first element as the identity element, and second element as the first 2 going to 3, 3 going to 2, the reflection. The third element also as reflection 1 to 2, 2 to 1. Fourth element, so the identity element is nothing but it's a reflection. It's 0 reflection probably. It's taking it as 0 reflection. So next is 1, 1, 2, 3 the cycle 1, 3, 2 and 1, 2, 3, 3, 2. No, sorry. The identity permutation is nothing but it's 360 rotation. The other reflections are 2, 3, 1, 2 and 1, 3. These are the reflections. Okay, reflections are 2, 3, 1, 2 and 1, 3. Suppose that we label them as reflections. mu1, mu2 and mu3. Row 1, row 2, identity. So we can achieve this using changing the elements command. So instead of using this elements command, let us give a list of the other names using which we want to construct the group table, and the other names are ID, identity. The second variable we know that it's mu1. Third variable we know that it's mu2. I don't know whether it's mu2 or mu3. 1, 2, 3. 2, 3 is 2, 3, 1, 2, 1, 3. Okay, whatever name you want to call. Mu2. The third one we call as row 1. Sorry, fourth one. Fifth one as row 2. And the sixth one as mu3. Suppose. mu2, row 1, row 2, mu3. How many elements are here? Oh, one extra bracket is missing. So we get it like this. And the good thing is that we may even use LaTeX notation is what I think. If you use LaTeX notation, what will happen? Here ID itself. Suppose we use mu 1. Will we get that? Yes. So if you want to get, directly typeset all these things, you can probably use the this notation and use the LaTeX command here. What will be the output? So you will get here somewhere. Where did I use? mu1. mu1 I will be getting as this. If I directly copy and paste this thing to any document, I will be getting that the usual mu as a symbol. So this is also possible. So that's the significance of this names command. So whatever label you want to use, instead of the usual label given by Sage, we can use this elements command for controlling that. In fact, we can find the multiplication table of certain specific elements itself. That's also possible. Which means that if you do not want to see the multiplication table of all the elements, suppose that you want to see the multiplication table of some particular elements alone, that's also possible. For example, suppose that we define S3 to be this, and suppose that you want to see the multiplication table of 1 to itself. So is that possible? 1 2 and suppose 2 3. So S3, I think the generators, if you use 1 2 and 2 3, you will be getting, I don't know what exactly you will be getting. Maybe I will try. So suppose that S5 is this, S5 is this. Suppose we choose 2 elements. This how I updated the Google document, symmetric group. No, I have not. So the group table of symmetric groups is updated in the Google document. Now suppose that we have this. Now suppose that we want to, okay, let us list the elements. See, the elements are here. Let us take just 2 elements. Yes, 5, 2. Yes, 5, 3. Okay, I don't know whether this 2 and 3, maybe I should use it like this. So these are the 2 elements, 1 2 and 1 4 2 5 3. So 1 to 4, etc. So if I want to see the multiplication table of these 2 things, that is also possible. The only thing is that I need to specify that I need to just declare this as a set. Suppose that H is equal to just this, the list of elements. Suppose H is this. Now print the carry table with elements from H. And names as, what are the names I should give? Maybe S5 2, names as names as elements. Elements are from this one. Shall I use multiplication table?
So first we generate a group and then only it can give us the table.
Sorry, read.
As H is actually H is a list,
Yes.
and then for any list it cannot give the table, carry table.
So what do you mean by actually the multiplication table? Multiplication table essentially means that so what I meant was that take the elements, the second element and third element as we have already taken, then 2 into 3, 3 into 2, that's it. That's what essentially I wanted. 2 into 2, 2 into 3. That's probably okay. Multiplication table, that's not probably the correct thing to do. I think it's not, I'm not doing the correct thing. So multiplication, even multiplication table, MULTA, multiplication table, elements from H.
First we find the group generated by H.
So we have not taken the group generate. So H is not actually a group. Maybe I should use a group itself. Okay, what you said is probably correct. So permutations we will take. Permutation group. Probably we can do it like this. What is the command? Permutation group generated by these elements. Okay, let us go that way. So that it will be a group. So let's try that way. In that case, H itself should be enough. So what is the previous command that we used? Carry table, right? Okay, in that case, I think this is enough. Even elements is not required. Permutation group generated by the two elements S5. These two elements are here.
I think name
List of element names must be same size as that of
names.
okay, names. I think we can simply let us just use the elements, so there is no confusion.
Yes.
Okay. For the other thing, probably that for loop itself is enough, but that is not actually the correct thing I wanted. I wanted to just see if we take two arbitrary elements, can we find the multiplication table of those two things? Of course, the multiplication table will be having some other elements outside that set, definitely, because if the set is not multiplicatively closed, it can happen. But I wanted to see if the multiplication table actually can be created or not. It seems no. So this actually doesn't seem to work. What I actually wanted doesn't seem to work. Symmetric group we define. H is just set of all. H is just two elements, S5 2 and S5 3. Now if I ask for the S5 multiplication table with elements from H. This is what I wanted. Elements from H without giving this parameter. This doesn't seem to work. Elements is from H and the options are here. This doesn't seem to work. Even Cayley table, let me just see even the Cayley table is working or not. Cayley table, I think it's only for the group, so that's not very, I'm not very hopeful about that. I think that's not working also. No, that is not working. So permutation multiplication, we are unable to pass that option somehow. Okay, let us, I don't know whether this will actually, this is possible or not. Order abelian, okay. So here what we are trying to do is we are generating. So by permutation group S5 2, S5 3, it actually generates. If we use, see here we have generated a subgroup, right? Here we generated a subgroup. That's not very useful. Okay, so probably it's not working anyway. So the generators command, have we already tried the generators command somewhere? Gens, okay, that we have seen. So this generators command is that generator command will work in the congruence ring also in the following way. Suppose that we take Z6 to be equal to this. I will copy and paste. Okay, this is not working anyway. What I wanted is not something I can of course achieve this using a for loop by taking the multiplication, but that is not actually wanted. I wanted Sage to give the multiplication table using those two elements as the top header. So that doesn't seem to work. So
earlier you have written a program also for the elements which are less than and prime to n.
Yes, that is correct, but on the it doesn't actually look like a group table because the top row was not coming properly.
Yes.
The top header row was, of course, the multiplication was coming perfectly, but if Sage itself is giving some nice command to do that, that would have been much better. That's what I thought. But that doesn't seem to work here somehow.
Yes.
Maybe we will try with some other group because I think the permutation multiplication is a different option. It is not actually the usual multiplication. Maybe because of that, it's not giving it like that. Probably. Let's try to see if we can achieve this in Z6 because multiplication is there. The usual multiplication is there. Not usual multiplication. It's modular multiplication, of course, but it is somewhat compatible with the usual multiplication. So let us try to see if that's working here or not. So what's the question? Is there a limitation of number of elements? So some question from YouTube. I don't understand what exactly you meant by, is there a limitation of number of elements in the Cayley table? I don't think that any limitation is there. The only limitation is your memory. That's a problem. So if your system is not good enough, if your memory is not good enough, then Sage may hang. That's a problem. So we.
Sir, is it possible to define a group here?
Defining, how do you define the operation you have to perform? That's what I'm wondering. So I will try to answer to that question. But as of now, we have been using only the. So if you, I think you may need to define your own operations there, right? That's the basic thing.
Yes.
Okay, define.
Suppose I define one operation, and what I want that Sage will find out whether with respect to that operation is it group or not.
Okay, so we can actually do that, but the technical thing. Okay, let me just try to answer that thing. So what you essentially want is you define your own operation, right?
Yes, I define one binary operation, and with respect to binary operation whether it is making one group or not. That I want to check.
So then for each and every element we need to define that, right? So so otherwise you need to define it generally. So
Suppose that integer set, and in the integer set I am defining some operation. Let's say x star b equals to a plus b minus 1, and with respect to this operation, whether it is a group, and if it is group, what is the identity element?
I think this is possible, but the only thing is that how complex. I'm just checking how complex that that operation is. Just 1 minute. I will just try to answer. I'm just finding out how to quickly do that. How to define. So we know that any group is actually what do you call it? It's a subgroup of permutation group, right?
Yes, sir. Yes, sir.
So so technically this must be possible. But the only thing is that you need to find what exactly is the isomorphism between your group and the subgroup of the permutation group is. That's what I'm wondering.
Yes, actually, we can find some subgroups generated by the elements, cyclic subgroups of any permutation group.
Cyclic subgroup, what is meant by that?
We can find list of all cyclic subgroups of S5 or S4. There is some command for that.
So list of all cyclic subgroup essentially means that you are taking so by cyclic subgroup you essentially mean that you are taking power of a single element, right? And go up to the order of that. So generating that is essentially equivalent to looping through all the elements and take the powers, and the only thing is that you need to filter out the duplicate subgroups.
Yes.
So
if we want to find, if we want to check any subgroup, then that subgroup is isomorphic to some subgroup of S5 or whatever we want to take.
okay, in fact, yes, I understood that.
The cyclic permutation groups 5. Suppose if we take F is equal to cyclic permutation group.
See, there is actually see, for creating cyclic subgroup, for that what you need to essentially do is, once you have already defined a group, for example, suppose that we have already seen two finite groups, the congruence group we have seen and the permutation group we have seen. Using the subgroup command, we can generate a cyclic subgroup. That is one thing. Okay.
Yes.
Using this, okay, something like this. Okay, let me just go into that thing. So we have already seen one example here. We were already dealing with which one? Symmetric group 3. Okay, let us take symmetric group 3 itself once again. Suppose we take this. Suppose we give it here. Now suppose that we take h to be equal to, we know the list of elements there. List of elements we can take 1, 2, 3 itself for S3 0, suppose. S3 1, suppose. S3, I don't know what notation we used, S3 1. Okay, this is 1, 3, 2. Now suppose that we define S3 dot subgroup generated by the list of elements S3 1.
Yes, sir. Yes.
Or just one element. Okay, let us see print h and what this is. Okay, this actually works. So this we are actually getting, but so what the question was that can we define a group? So what I immediately thought of was that every group is actually a subgroup of the permutation groups. Okay, that's one thing. Every finite group, that's definitely going to be easy to find. So, but even for that, you need to define an isomorphism and find out what type of group it is. So, it must be possible because Sage must be already doing that. Sage must be finding an isomorphism between two of them, and but between two random groups. So between two not randomly arbitrarily defined groups. So how to define the operation first of all? That's the first question. How to define the operation in SageMath? So we can define the operation as a function, but if you define it as just as a function, that may not work because that will give some trouble for us. So alternating group, simple group, alternating. Just I'm checking that documentation to just see if there is some quick answer to that or not. It says that it's possible. It says that it is possible to define our own thing. But what I'm thinking is how to get a quick solution instead of free group about generators, homomorphism, HGen, free group, finally presented. So we need to essentially define. Okay, just 1 second. I'll try 1 more minute and try to find out the answer for that. Defining. Okay, there is actually one way it seems. Group size of type 3 define. So many of these already available groups are predefinedly available. They're predefined and they are available here like most of the groups. But what about define group operation?
Even see, sir, we can find the list of all subgroups of S4 or S5 from which we can take those subgroups which are isomorphic to
Then we need to check the isomorphism. Then we need to check the isomorphism. Then we need to define the isomorphism. Listing the that must be easy. The group subject may be used in various groups. So the listing the groups must be easy, as we have already seen. That what we need is so the already available groups are permutation groups are already there, and matrix groups are already there. So integer groups are already there. These are some known class. So after that, what you can do is how to define groups. Okay, I will try to find out an answer for that thing. So how to define arbitrary groups and how to what was that? How to define arbitrary group operations, right? So there is already a construct called group. So the group G is equal to group. So how do we define a group? That's first thing. This group is there is a class, it seems, for creating the group, but how to actually implement that thing is what I'm wondering. How to implement that in the usual thing. And now one more thing is that how to check the what you call homomorphisms. How to check the isomorphisms or homomorphisms.
Sir, if we take order of elements, then we can check, means if orders.
But order of the elements, order of the element. Okay, that is only a negative test in the sense that if we have different number of elements having same order, that's they are not isomorphic. That's the only thing we can say, isn't it?
Yes, sir.
So that is not actually a what do you call a positive test.
Yes.
So the only thing is that this is the only result probably most probably we can make use of, and most probably Sage also will try to implement. Like see, most of the groups, we know that most of the abelian groups, they are going to be in some way isomorphic to most of the finite abelian groups are direct products of Zn, right?
Yes.
Finite abelian groups are going to be direct products of Zn, and other groups are going to be again they are all subgroups of permutation groups, definitely. So how to find out to which permutation group it's isomorphic to, and in that way probably we can just rename the elements as we have already seen using names of elements in that, and we can try to do that. So if we use that technique, just one second, isomorphisms. These are all usual already available groups. So symmetric group, that's already defined. Symmetric group is defined now. Subgroups also we can probably find. So as we have already seen, all the subgroups we can list. Listing the subgroup, it's quite possible. For example, suppose that S3 dot subgroups. I think this should list all the subgroups is what I think. Yeah, this is here. So if you list these are the subgroups that we get. Subgroup generated by identity, subgroup generated by 2, 3, and of course you can loop also through. For example, suppose that for you can see all subgroups like this. For H in, suppose that we loop through, print list H. So these are the subgroups of these are the subgroups of S3. Is it correct? How many subgroups this has? S3. I think subgroup. These are not subgroups. Actually, subgroup generated by, I guess.
So we may take H dot order. H dot order, then it will give an order of all the subgroups. Yes, sir.
So these are all subgroup generated by, not actually subgroup itself. Yeah, order will definitely give. So this command is not very useful. Order 1, order 2, order 2, order 2, order 3, order 6. So all these subgroups are here. Of course, but still the question is that we cannot check how to check if two groups are, if one particular group that we have taken is isomorphic to a permutation group is still a difficult question, because even for that we need to define the group operation. So manually we may be able to do that, but doing it programmatically using Sage, that's the question. So many of the already known groups actually can be created directly because using certain commands like subgroup, alternating group, all these commands actually can be used. Cyclic permutation group, all these things are useful for creating what you call subgroups from non-groups, but these operations are all non. Okay, these operations are all non. We are not trying all these things on any of the arbitrary things. So
as you have earlier defined composition table or tally table.
yes, what you want to say is we can compare.
If we have any finite group and if we construct a Kelly table, then from that Kelly table
Yes,
we can
so
apply the
that is actually a good thing. That is actually one thing that we can try. So for that, what you need is we need to define the group operation using some def command or a function, and after that, suppose that we create the Kelly table as a list. Okay, suppose that we create the Kelly table as a list, and the corresponding element, suppose that we take from the permutation group of same number of elements with the same number of elements. So if we can compare this with, see, even that we cannot completely say, because suppose that we have a group with elements 5 or element 6. Okay, we don't know that this element 6 group is actually going to be a subgroup of S6 or S12, or that how can we confirm even that?
Yes, so it's not easy.
It's not that easy, because so for randomly checking whether it is a subgroup of some group or not, we need to first of all fix which permutation group we are trying to, because there are infinitely many permutation subgroups, infinitely many permutation groups, symmetric groups, and therefore infinitely many subgroups having the same cardinality possibly. So the random trial and error checking is not actually going to work, is what I feel. Of course, the Cayley's theorem is there. The Cayley's theorem actually gives you a way to construct from a group we can actually construct a permutation group. That's one possibility.
Yes.
Cayley's theorem is the theoretical answer for that thing. Okay, we'll try to see if that's possible, but it seems that it's possible, and maybe Sage is also trying to implement the arbitrary group table, arbitrary group construction using Cayley's theorem itself. But that probably needs a little bit of tweaking. As of now, I don't know how to exactly do that, but the documentation of one of the Sage help files says that it's possible, but it's not concretely described. We'll try to see that, if it's possible or not. Okay, I think, of course, there are many other things many other constructs available in abstract algebra, many other things we can construct using this. So, a very good tutorial called Sage for Abstract Algebra is available in the internet, which you can probably try. I was also making use of that particular tutorial. So many other things like many of the very well known results in group theory like Silo theorems, Lagrange's theorem, and all such things are actually discussed. Finite fields, Galois theory, all these things are actually being discussed in the Sage for Abstract Algebra, that particular textbook. That text is by Sage for Abstract Algebra by Robert Beezer. So this textbook is probably useful. I'll share that. Maybe I will put that in this worksheet itself, so that Sage for Abstract Algebra by Robert Beezer. I think it's a freely downloadable book. So this is actually a good beginning, not good beginning actually, it's a very good book describing several things, how to make use of several commands in abstract algebra, including going up to Galois theory. So many of these things are possible, and we will try to do some problems also towards the end of this workshop, when we have a problem solving session where we try to do this isomorphism related kind of stuff, as well as the defining arbitrary group. I think it should be possible, but mainly, most probably, most probably I think it's going to be by establishing an isomorphism with some permutation group. There must be a way. So that's what I think. So with this, probably we will stop today's session, and trying to discuss something in operations research tomorrow, and I will try to answer this abstract algebra question as well, if possible. So if there are any questions other than this isomorphism construction, which I don't know as of now, if there are any other questions, maybe I can try to answer. Thank you.
So, sir, where have you written that book, the workbook, in the Google sheet?
Yes, in the worksheet I have written. When I am sharing this worksheet, you will be able to see that.
Okay.
Because I will be saving this to the Google, Google Drive, so that you can download this.
Okay.
This is a freely downloadable book. It's a very good book, and of course there are several other books also related to abstract algebra, but this one I found to be somewhat much more comfortable and dealing with most of the types of already known familiar groups. Not all groups, of course, not all abstract groups, but already known familiar groups like integer groups. All such things are already handled in this. So let me share the feedback link once in the just 1 second. So maybe we can wind up today's session, and we will meet tomorrow at the same time, 6 o'clock.
Okay, sir.
Thank you. Thank you, sir. Thank you.
Okay, thank you very much.
Thank you, sir.